Hi and welcome back to the next in the series on vine copulas, and having looked at conditional copulas, conditional distributions, we're now ready to look at how you can actually fit a three-dimensional vine copula. Now, this is important because, for a start, it's what we've been trying to do since the beginning, really, to work out how to fit data to a vine copula. So it allows us to see how you take that data, how you fit it, how you measure that fit, and see whether it's better or worse than another fit, which is really important. But also it gives the building blocks for how we fit data to more complicated copulas, because the principles are pretty much the same as here. The kind of decompositions we've looked at before are pretty much the same as they are for a three-dimensional vine copula. They just get a little bit more complicated, but it's exactly the same principle. So let's get started. So what we're going to do is we're going to take some data and we're going to fit various distributions to that data. We're going to calculate the likelihood functions, and we're going to use these to compare the fits of the distributions that we're looking at, so we can see which is better, which is worse. And the two approaches we're going to use are a multivariate normal approach, and then one where we've just got normal marginal distributions, and we've got Clayton copulas for all of the or both of the pair copulas that I'm going to be using in my vine copula structure. Now, I'm using just one type of copula. There's no reason that you have to use just one type of copula in a vine copula structure, even for the conditional copula that you need to calculate. In fact, one of the reasons to use a vine copula is that you've got the flexibility to use as many different types as you want. But the Clayton copula is a pretty easy one to use, so it makes sense to just keep everything to that simple single copula for now, and make the examples quicker to go through and easier to follow. So for the multivariate normal distribution, when we're fitting that, we can actually find f of x1, x2, x3, that joint density function. We can find that directly, and that's what ends up getting plugged into the formula for the likelihood function. For a vine copula, however, we need to use the decomposition f of x1, x2, x3 is equal to f of x1, f of x2, f of x3, so the three marginal distributions, times c of u1, u3, times c of u2, u3, so that's the copula density functions between 1 and 3 and between 2 and 3, and c of u1 given 3, u2 given 3, so that's the conditional copula between 1 and 2 given 3, which is the variable we know is joining them. So I'm going to do this in Excel, so you can see exactly what's going on, and going to be using 120 months of equity return data, and three of the banking stocks that I used in previous examples when I was trying to work out what the structure of a more complex vine copula might look like. So the first stage is to decide the structure using Kendall's tau. I'm not going to go through calculation of Kendall's tau. I've done that before, and as we've seen, it takes a lot of space and a lot of time, so I'll spare you that. I did it so you don't have to. What we can see from this is that the highest values of Kendall's tau are between A and C and B and C. So what that suggests is that C should be the central node, and both A and B should be connected to C rather than to each other. So this gives us our the shape of the vine copula that we're going to be using. So, first stage, our starting point is to calculate the log likelihood for a multivariate normal distribution using the data that we have for these three banks, Bank A, Bank B and Bank C. The first column, column B there, and the first is the data, the returns for the first bank, Bank A, and we have there the average return for those, and also the standard deviation of the return, so the mean and the standard deviation, expected return, volatility. And we do that for banks A, B and C. We also look at the correlation, so that's the correlation between Bank A and itself. The rest of the correlation matrix is slightly more interesting than that, and these are obviously Pearson product moment correlation coefficients, not Kendall's tau, because that's what you use fitting a multivariate normal distribution. Now you'll see what I've done as well is I've taken the standard deviations from B4 to D4, and I've just copied those across into H5 to J5 and F7 to F9. And the reason is, if I multiply the correlation by the appropriate pair of standard deviations, I then get the covariance matrix, which again is what we need to plug into our probability density function for our likelihood function. It actually goes into that formula as a matrix inverse, so I calculate a matrix inverse, and also we need to calculate the determinant. What actually gets used in the formula is the determinant raised to the power of -1/2, so 1 over the square root of the determinant. So that's what I've calculated here. Now, when looking at the multivariate normal density function, the first thing you do is you take the return for each asset class, or for each stock, and you deduct the average return for that. So I do this as a kind of preliminary stage here. So I've got A minus A bar, B minus B bar, and C minus C bar. And that's essentially just taking the returns in each period and deducting the appropriate mean. And then all of this gets put into this formula here, the multivariate normal density function. And that gives me the density for those 3 points, given the correlations that I have, given the means, and the standard deviations. I do that for every trio of data points that I have. Now that's the likelihood. What I want to calculate is the log likelihood, because I can add those up. As you remember, the likelihood function is the product of all these density functions, whereas if I use log likelihood, it's just the sum of the logs of these density functions. So I simply take the log of that, and then I sum them all in R4, which gives me that number of 472. So that is our starting point. That's the likelihood, or the log likelihood function for this data fits to a multivariate normal distribution. So to recap, the log likelihood for the multivariate normal function is 472.41. And that was done just by simply taking the data and sticking it through the density function for the multivariate normal. For the copula, I use the IFM approach, the inference functions for margins approach. And this involves fitting the marginal distributions, the marginal densities first, then taking those as given, and then fitting the copula separately. So stage 1, fit the univariate marginal distributions, and I'm going to assume they're normal, and calculate the log likelihoods for these, and just keep that number. Then fit the copula, and calculate the log likelihoods for the various copulas I'm using, add everything together, and this gives me a number which I can then compare with a multivariate normal fit. And that's the reason for doing it, because I mean, a lot of the time when you're thinking about fitting a copula, you might think, well, I'm just fitting the copula, why would I want to care what is happening with the density functions? Because the point of a copula is you're starting with the distribution functions for the marginals anyway, so why do you really care what the fit is? And the main reason, I believe, is if you wanted to compare the fit of your copula with a multivariate distribution, such as the multivariate normal or multivariate T, you've got to have the marginals in there somewhere. So you've got to be looking at the likelihood of the marginals plus the likelihood of the copula to compare it with the likelihood for your multivariate distribution. So univariate normal should be pretty straightforward. It doesn't take up much space, and what I'm doing here is I'm calculating the likelihood summed over, or rather sum of the log likelihoods for the 3 univariate normal distributions that I'm fitting. So here again I've got the average and the standard deviation for assets or for banks A, B and C. Calculate the likelihood with a much more straightforward formula which will be familiar to anybody that's done some statistics. That's just the normal density function. Do that for A, B and C. Take the log, do that for A, B and C and for all the observations. Sum them, and then sum the sums. And what that gives you is the univariate, the log likelihood function summed over the 3 univariate normal distributions. So the log likelihood for the marginal distributions is 399.02, and this is what then gets added to the copula likelihoods. So copula likelihoods, just using the Clayton copula. Got the data here, and it gets a little bit more involved, partly because I've got to go back and forth a little between the data. But what I've got here for starters is I've got XA, XB and XC, and these are This is just the return data. So this is our raw return data. What I want to do first is I want to turn this information into uniform distributions. And the way I do that is I take the rank of each observation relative to the rest of the observations for that variable, and I divide them by the number of observations plus 1. So I will always end up with a number which is greater than 0 and less than 1, and is uniformly distributed. So that has transformed XA into UA. And I do the same for B and for C. Then I move over to the correlation matrix. So this is a Kendall's tau correlation matrix, and as you can see, I've got the correlations between UA, UB and UC for Kendall's tau, and I've also got the correlations between U of A given C and U of B given C, just off to the side there, which I will need when I'm calculating the conditional copula. So, as you'll recall, it's the correlations between A and C and the correlation between B and C. Those are the two biggest ones. So those are the ones which I use to fit my Clayton copulas. So my pair copulas are between A and C and between B and C. So fitting a Clayton copula, if I'm using the method of moments, there's a handy relationship which I've written down here in EL13, which is that Kendall's tau is equal to the alpha for Clayton's copula divided by alpha plus 2. So you can rearrange that and say that the alpha for Clayton's copula is equal to 2 times Kendall's tau divided by 1 minus tau. So knowing this and knowing these values of Kendall's tau, I can therefore come up with a parameter for the Clayton copula, the Archimedean copula, Clayton copula. And that's what I've done. 2 times Kendall's tau divided by 1 minus Kendall's tau. So that gives me the value for the parameter for the Clayton copula for the copula between A and C. I do the same for B and C, and I also do it using different correlations for that conditional copula at the end. So having got Kendall's these parameters for A and C and B and C, I can then calculate the conditional numbers that I need for the uniform distribution that gets plugged into that conditional copula, so U of A given C. Now if you remember, I work that out using an H function, and this is what the H function looks like for the conditional copula. So this is H, so U of A given C is the same as H of A comma C. So it is A conditioned on C. And this formula here shows you what the H function is. And as you can see, to do it, you need to have the parameter alpha from that copula between A and C. So I'm taking that and I'm using the uniform distributions for A and C to calculate that H function. And I do the same for U of B given C using the second Kendall's tau that I used to, rather using the second alpha that I calculated from the Kendall's tau between B and C. So that's all of my uniform distributions that I need, and that then allows me to fit my copulas, the copula between A and C, the copula between B and C, and the copula between A given C and B given C. So this is where all that hard work happens, and the first thing we've got is the copula density function, which for Clayton's copula is relatively straightforward. And as you recall, that is calculated by taking the copula distribution function and partially differentiating it with respect to UA and UC. So we take that, that also uses alpha as an input, and the value there, ES4, you'll see is just copied over from EM16. It's actually a transpose of those 3 values of alpha from EM16 to EM18. So that gives us our copula density. We then want to take the log of that copula density, and we want to do that for all of those 3 copulas, and we want to sum those across all of the data points and all of those three copulas, and doing that we get that value of 133. Adding that to the marginal fit, so the log likelihood for the marginal density functions gives us our final number, which is 532, which, as you'll recall, is bigger than the likelihood that we had for our multivariate normal distribution, which means it's a better fit. Now, we could actually try to improve it even further here, because what we did was we calculated the values of alpha that go into our fit using the method of moments. But because we've got this formula, what we could actually do is we could say, well, let's use Excel Solver, and we'll try to maximize the value of EY2. So we'll try to maximize that likelihood function by altering ES4, ET4 and EU4. So we'll see if the maximum likelihood values for those parameters are slightly different to the ones that we find from method of moments, which they might be, because we have got this conditional copula, which complicates matters a little bit. So on the face of it, univariate normal and Clayton copula wins. So there you probably want to use the Akaike information criterion or Bayesian information criterion or likelihood ratio test to confirm this. But you're looking at log likelihood of 532 versus 472. It looks pretty convincing. Now, as I mentioned, you can also find the parameters for the Clayton copula using maximum likelihood estimation, and this does result in a small improvement in your likelihood number. It goes up from about 532 to 535, and these come from some fairly small parameter changes. So the alpha for the copula between A and C goes from 1.81 to 1.79. The alpha for the copula between B and C goes up from 1.5 to 1.71, and for that conditional copula drops from 3.22 to 2.79. So fairly small changes, but enough to give you a slightly better fit, and just demonstrate that if it is maximum likelihood that you're interested in, you do get slightly different results than from method of moments. So there you have it. That's how we can fit a three-dimensional vine copula to the data. And if you do want to move to more complex R-vines, it's pretty much the same principle. The only thing you need to work out is the exact decomposition each time, and how things look in terms of the conditional copulas that you're going to have to evaluate. And it's not necessarily straightforward, but it really is not much more than an extension of the technique which I've just shown now. So we'll have a look at some of those more complex copulas and those more complex decompositions in the next video.